I'm Mike Morrow. I'm president of the St. John Center of the RASC. I'm going to start with an acknowledgement. We respectfully acknowledge the province of Newfoundland and Labrador, of which the city of St. John's is the capital city, as the ancestral homelands of the Beothuk. Today, these lands are home to a diverse population of Indigenous and other peoples. We would also like to acknowledge with respect the diverse histories and cultures of the Mi'kmaq, Inuit, and Southern Inuit of this province. So our speaker today is Mahumm Ghaffar from, she's a PhD student, based, a Mahumm PhD student. She's based in at Grenfell, and she's going to be talking to us about dark matter. Can you see my little mouse moving around there? Can I point with that, or anyways? We'll do some observation reports. The observing chair will run us through the sky next week, do a little bit of news at the end, and then we'll, if there are questions from members or visitors about new equipment or anything else they want to ask about, that's something we can do at the end. I'd like to welcome any visitors that are here, and point out that these meetings are open to the public the third Wednesday of every month, except for July and August. And to get the link, if you want to keep coming, you can just keep asking Randy by emailing info@stjohnsrasc.ca. And the meetings are open. You don't have to be a member. If you become a member, there are some benefits, although you're hearing some complaints about some of them. There's a supportive community here ready to help you learn about astronomy. We'd be supportive even if you're not a member, but it probably makes it a little bit easier. There is a member chat group where people share observations, discussions, alerts for things that are going on. There are publications, Sky News, a journal, which I've shown down here, the Observer's Handbook, which some of us have gotten and some have not. There are low-cost equipment rentals. Chris Stevenson's the equipment director. I think I've got it right, 7 telescopes, a solar telescope, lots of accessories. So that's a good way if you're thinking about getting a piece of equipment to try something out that's similar. When things become a little more normal, hopefully we'll have some more member observing sessions, and there's a way to join the RASC. And one thing I wanted to mention is that if you are a member, you should be getting an RASC newsletter. You don't have to be a member to get that. You can write to the RASC and subscribe to that. And it sort of says what's happening at the RASC, but also things about events, things to look for in the sky. And so that's weekly. And there is a bulletin that you should be getting monthly. So if you are a member and you aren't getting those, again, you could let us know at the info website, or you could try a trouble ticket at RASC. But hopefully people should be getting that. And that's one of the places, along with Marcellus and Randy. Marcellus is our National Council representative, and he's been, while we've been having trouble getting stuff, he's been very helpful in communicating with the national office to find out what's going on. Even today, I think he was in touch. And so he's getting us a lot of information, but you can also get some information about things that are happening on the national level through these newsletters and bulletins. Okay, so with that, I'd like to introduce our speaker, Mahumm Ghaffar. And as I said, she's a PhD student. Her area is theoretical subatomic physics. Her supervisors are Svetlana Barkanova and Alexanders Alexeyev. She obtained her, so she's based at Grenfell. She obtained her master's from Quaid-e Azam University in Pakistan, did a one-year postgraduate diploma at the International Center for Theoretical Physics, which I think is in Trieste, Italy. Very well-known place. And she's going to talk to us about dark matter, the hidden mystery of our universe. So I'm going to stop sharing and ask Mahumm to go ahead and share her screen. So take it away. It's all yours.
So thanks, Dr. Michael. And I would also like to say thanks to Royal Astronomical Society of St. John's for organizing this talk. So today I'm going to talk about dark matter, the hidden mystery of our universe. Okay, so first let's talk about the stuff which we can see in our universe. So first thing is humans. Of course, we are all humans and we can see each other. Even right now we can see each other, though virtually not in person, but we can see each other. Then we can see the animals and plants, or in general, we can see anything which is on Earth, like oceans and forests or whatever stuff is on our Earth. And also we can see our beautiful satellite, the moon. Then not only the Earth, we can be able to see the sun every morning when the sun rises and sun sets. And also we can see some other beautiful planets of our solar system, like Mars, Jupiter, Venus, and if the sky is clear, maybe you can see Saturn. Or with the help of course, telescopes, we can see all our 8 planets of our solar system. And not only our solar system, we can be able to see other stars which are present in our galaxy. So we are living in Milky Way galaxy. And just like sun, which is a star, there are many other stars in our galaxy. And in a clear, dark night sky, you can see all those stars which are in our galaxy. And not only our Milky Way galaxy, but by the help of very powerful telescopes, we can be able to see the other galaxies which are comprising this whole universe. But you will be surprised to know that all that stuff which I just talked about, the stars, planets, galaxies, everything, that is only the 5% part of our universe. So everything which we say that the universe is made up of, it is only the 5% part. So if that stuff is just 5%, the question arises, what is the universe made up of? So the thing is actually the universe, which we know, is not only made up of stars, planets, and asteroids, etc., but there is a lot more to the universe. According to physicists, universe is thought to consist of 3 types of substances. So first one is the visible matter, which I just talked about, like we all humans and the stars and planets and all that stuff, which is just the 5% part. So that is made up of atoms. The remaining around 30% part of the universe is thought to be consisted of dark matter. And we will talk about that dark matter, what it is. And the remaining roughly 65% part of the universe is thought to be made up of dark energy. Both these dark matter and dark energies are very strange, and that is why we call them dark. So dark energy, which is around 65% part of the universe, it plays a very vital role in our universe. And but I will not talk about this dark energy today in this talk. My focus is about this dark matter, which is around 26.8% part of the universe. So as the name suggests, it is matter. Dark means we can't be able to see it, but this is matter. It clumps together, and it has there are some facts which people now know about the dark matter. So first fact about dark matter is that in the realm of physics, dark matter is relatively new. It was first hypothesized less than 100 years ago. So if you compare it with the other, visible matter stuff like atoms, electrons, protons, all these particles, that theory of dark matter is comparatively new. Then another fact about dark matter is that it doesn't interact with any electromagnetic radiation. Here, I would also like to say that the term dark is a little bit confusing, and some physicists don't like this term. Because usually when you say that something is dark, it means that it absorbs light. But in case of dark matter, it doesn't absorb light. It doesn't interact with light or any kind of electromagnetic radiations. all these radiations, even our visible light, it actually passes through this dark matter. I think the better word for that matter should be transparent matter, because it doesn't interact with light at all. And that is the main reason that we can't be able to see it, because it doesn't interact with the visible light or any kind of electromagnetic radiations, whether these are X-rays or gamma rays or any kind of rays. And that is the main reason we can't be able to see it, or by either with our naked eyes or by the help of any telescope, because it doesn't interact with any kind of electromagnetic radiations. And another fact about dark matter is that because of its mass, because it is matter, it's massive, it has gravitational effects. And that is the main reason, because of the gravitational effects, they help this dark matter to hold the universe together. So because dark matter is massive, it is literally the matter, so it has gravitational field. So only these are a couple of things which people could say 100% about this dark matter, but other than that, we don't know anything about this dark matter yet. So if we don't know dark matter, how we can be able to probe it? So there's some other stuff about dark matter. So there's a famous quote about dark matter. So Fabiola Genotti, who is the Director General of CERN, according to her, dark matter is everywhere, in this room, everywhere. And that's actually true, because dark matter is in such a big amount. It's around 26.8% part of the universe. So it is literally everywhere. Even it is possible, like right now we are talking and sitting in our room. So it's possible that millions of dark matter particles are passing through us and they are present in our rooms. But because we can't be able to see it or we can't feel it, so we are unaware that it is here. But if it exists, it must be everywhere. Then dark matter interacts with gravity because, like I've said, it is matter, it is massive, so it has gravitational effect. And its mass has actually the gravitational effect. It bends light traveling through the universe. And that is partly how we know it exists, because it bends the light. So it doesn't interact with light, but because of its gravitational effect, it can be able to change the path of the light. And this is one fact that people know, that how this dark matter should exist in our universe, because they saw that effect of gravitational lensing, the bending of light by this dark matter. And according to Vera Rubin, who is a famous astronomer, and she actually was one of the first people who discovered that dark matter, in a spiral galaxy, the ratio of dark to light matter is about a factor of 10. That's probably a good number for the ratio of our ignorance to knowledge. We are out of kindergarten, but only in about 3rd grade. So there is a lot more to know about this dark matter. So because dark matter is so important, it is present in such a big amount in our universe, and it is a reason, because of its gravitational effect, it is kind of glue that binds galaxies together, and it's everywhere and all around us. Yet we know nothing about it. So in order to engage public and to aware public about the presence of dark matter in our universe, international collaboration of particle physicists wants to give a voice to the silent, unseen, and massive presence of dark matter. And the ultimate aim for, so every year, actually, the particle physicists collaboration, they celebrated a dark matter day in order to aware public about the presence of dark matter, so that they can drive more international support and relay more brain power for their dark matter experiments and theories that ultimately will lead to a discovery of epic proportions. So every year, this dark matter day is celebrated internationally since 2017. First, it was celebrated in 2017. And since 2017, more than 159 global, regional, and local events have been held on and on around October 31st by institutes and individuals looking to engage public in discussions about what we already know about dark matter and the many experiments seeking to solve its mysteries. And now every year, the world celebrates the historic hunt for the unseen something that scientists refer to as dark matter. So now, if we don't know anything about it, about this dark matter, how we can be able to probe that dark matter, and because we can't see it. So if we can't see dark matter, there are some questions which the scientists or physicists even whether they are particle physicists or cosmologists, they are trying to figure out. So one of the main question is that, what is dark matter? Like what it literally is, what kind of stuff it is that we can't see. Is there more than one type of dark matter? So that is the question which particle physicists are in particular trying to figure out, that whether it is just one kind of particle which is creating this whole dark matter, or they are different particles, because our visible matter, which we can see, which is just the 5% part, it is actually supposed to be made up of 12 fundamental particles. And then, so in particle physics, there are 12 fundamental particles which are making all that matter around us, along with 4 fundamental forces and 1 Higgs boson, which is recently discovered. So because this visible matter is made up of different types of particles, so now the particle physicists are trying to figure out whether this dark matter, just like visible matter, it's made up of different types of particles, or there is just one kind of particle which is creating this stuff. And what roles did it play in the formation of structure in the universe? So that is actually the question which now cosmologists are trying to figure out. And are there other relics from the early universe awaiting our discovery? And will its discovery changes our present understanding of the universe? So these are some questions which cosmologists are interested, because we don't know whether the dark matter was, as we know that at the time of Big Bang, when Big Bang happened, our universe was created. So we don't know whether this dark matter was also created at a time of Big Bang, or after some time when the universe cools down, it was created after that. So there are some questions which are of interest for the cosmologists. Now let's talk about some first evidences about this dark matter, how people say that there is a dark matter present in our universe. So in 1930s, astrophysicist Fritz Zwicky realized that the galaxy clusters must contain a lot more mass than was actually visible in order to act the way they do. So here in the right-hand side of the screen, there is a very beautiful optical image of Coma cluster of galaxies. Coma is just the name for this cluster of galaxies. So in astrophysics, actually, we have some theorems. One of the theorem is known as the virile theorem. And the galaxies which are supposed to be stable, they should satisfy this virile theorem. And according to that theorem, potential energy should be equals to -2 times the kinetic energy for stable galaxies. So U is actually the potential energy, and K is kinetic energy. Formula for kinetic energy, as we know, is half mv square. V is the velocity with which that cluster of galaxies is moving. And if you talk about two particular galaxies, the potential between them, which is the gravitational potential, is represented by -a times gmm over r. A is a constant, G is gravitational constant. And these one mass, capital M and small m, so these are the two different masses of two galaxy clusters, and r is the potential distance between the two galaxies. So now when you substitute kinetic and potential energy values in virile theorem, U equals to -2k, you will see that this mass is equals to V square R over AG. So here we can, A is a constant, like I said, G is a constant, gravitational potential constant. M is the mass of the galaxies, which astrophysicists can be able to figure out, and R is the potential distance between the two cluster of galaxies, which they can also figure out. So when you substitute these values in this formula, you can be able to find out this velocity with which the galaxy is moving. So they get two values of velocity. First is the Mayer velocity, which was actually obtained by measuring the mass of the velocity and the potential distance between the galaxies. Sorry, mass of the galaxy and the potential distance between the galaxies. So that was the measured velocity which they figure out. And second one is the calculated velocity. So calculated, like they didn't measure it, but what they saw, according to that, they calculate the mass of the galaxy and the potential difference between the galaxies. So they calculated these two values. They got two values of velocities, measured and calculated one. And when they compared these two values, they saw that the measured velocity was much greater than the calculated velocity. And from here, they concluded that mass which they considered was actually too small. So, and that is the reason that the measured value, which was the actual value, appears to be very large than the calculated value. So that means we were missing something in our calculations. We were not taking this mass because the mass which we just substituted here was the mass which we can see in this cluster of galaxies. That was not the actual mass, and we were missing some mass. That is why the velocity appeared to be small. And from here, they concluded that there is something in this cluster of galaxies which we were missing. We can't be able to see, but it is there. It is some massive thing should be there to get the actual result, the measured result. And that thing was supposed to be the dark matter, which was invisible. Then another evidence about dark matter that was discovered in 1970s by astronomer Vera Rubin. So she discovered that the stars at the edge of a galaxy move just as quickly as stars near the center. So as an analogy, you can see here on the right-hand side, that is a beautiful image of our solar system. So here, this is the sun, and then we have our planets. So as I think most of the people, you know that, the closer you are to the sun, the greater will be the orbital motion or the orbital period of the planets. So for example, the closest planet to the sun is Mercury. It revolves around the sun, of course, or you know that all the planets, they revolve around the sun. And it took Mercury 88 days to complete its orbit around the sun. Then the next planet is Venus, and it took Venus 224.7 days to complete its orbital motion. And then we have Earth. We know that 1 year is 365 days. So around 365 days, this is the orbital period of the Earth. And as you go away from the sun, like the planets which are far off, like Neptune, Jupiter, Uranus, it took more time for them to complete one orbital period around the sun. The reason is because of the gravitational force. The further you are from the massive object, your gravitational effect will decreases, and the speed of the planet slows down. But if you are near the massive object, we have greater gravity, and that is why the planets, they move with faster speed. So not only our solar system, but we know that all the stars in a galaxy, they revolves around the center of the galaxy, because center of the galaxy is very, very massive. We have supermassive black holes which are at the center of the galaxy. So all the stars, they revolve around the center of the galaxy. So because center part of the galaxy is massive, so the stars which are near the center of the galaxy, their orbital period or their speed should be greater as compared to the stars who are at the edge of the galaxy. But what they observed was totally the opposite. They noticed that the stars which were at the edge of the galaxy, they were also rotating as quickly as the stars near the center of the galaxy. And why it is so? Because it means that there is something massive at the edge of the galaxy, which we can't be able to see. And that missing something should be the dark matter. So people call it dark matter because we can't be able to see that mass, but it should be there. Otherwise, there was no reason that why those stars which are away from the central part of the galaxy, they are moving with such fast speeds. So that was another evidence about this dark matter, that it should exist in our universe. So now there are, because we are trying to figure out what this dark matter could be, first is thought two possibilities for what sort of matter may make up of that missing mass. First is that it may be just a regular matter, just like our visible matter, but it's just not hot enough to be emitting any radiation, and that is why we can't be able to see it. So that is one hypothesis. Another one is that it may be some sort of exotic matter, not among any kind which we have naturally here on Earth, but there's a chance maybe one day we can be able to create it in our particle physics labs, which people are these days are trying to create that exotic matter in our labs. So far, what we only know is that dark matter makes up most of the universe, and it behaves like regular matter as far as gravity is concerned. So gravitational effect is the same. There's no difference between the dark matter and the visible matter as far as gravity is concerned. But other than that, we don't know anything about it yet. So physicists, of course, we can present different hypotheses about that dark matter. So there are some possible candidates about dark matter according to the particle physicists. So first thing which particle physicists thought that maybe the dark matter is WIMP. WIMP is a short form of weakly interacting massive particle. It is a hypothetical particle. It is not discovered yet, or it's not created in our labs. But in theories, we just came with this idea of that hypothetical weakly interacting massive particle. First, it was proposed by supersymmetry. So I will not go into the details of what supersymmetry is, but I can just tell you that, like I've told you, in the visible matter, which we know, so according to particle physics, all that visible matter is made up of 12 types of particles. And supersymmetry is known as the extension of that concept. So there is a standard model. Standard model says that we have 12 particles which are creating that whole matter, or that whole visible matter. And all those particles are, they are well proven. We know them. They are, we can create them in our labs. So we know that these 12 particles exist in nature and they are creating all that stuff. Supersymmetry is the extension of the standard model. It says that all these 12 particles have superpartners. They are different from their, particles, the superpartners, by means of the spins. So for example, if a particle has spin half, its superpartner will have spin integer spin. So if particle has half integer spin, superpartner will have integer spin, and vice versa. So that was a little bit idea about that supersymmetry theory. And this WIMP was first proposed by that supersymmetry theory. But WIMP is actually, it is, as its name suggests, it is weakly interacting particle. So people thought that it interacts with the visible particles, like visible matter, but it interacts very, very weakly. That interaction is so small that we can't be able to predict it or create in our labs. So they barely interact with the regular matter and they don't emit light. So that is why people come up with the idea that maybe that WIMP is a dark matter. Lightest supersymmetric WIMP is considered to be the most suitable dark matter candidate because it doesn't decay since it was created in the early universe and rarely produced a detectable signal, which is again the property of dark matter. So that is why people thought maybe that WIMP is a dark matter candidate. Then also, not only that, but there was a WIMP miracle. And according to that miracle, what happened was, theoretically, people calculated the number of lightest supersymmetric WIMPs. And that number, by chance, matches closely to the experimentally observed dark matter amount. So that was quite a miracle. And that is why people thought that if these WIMP particles existed, if one day we can be able to create them in our labs, then there's 100% chance that these WIMPs are actually the dark matter particles because their calculated amount matches with the experimentally observed dark matter amount in our universe. So that is the main reason most dark matter experiments are searching for these WIMPs, weakly interacting massive particles. As after years of development, we have now built detectors that have a chance of catching a glimpse of these particles. So the experiments, I will come later on in my presentation, but kind of experiments are running these days to get these, or so that we can be able to observe these particles in our labs. Another possible dark matter candidate is known as Axion. So this Axion is not actually the washing powder detergent. I didn't mean that this you can be able to see the washing powder, the dark matter in your washing powders. But there's a fun fact about this name Axion. Axion is again a hypothetical particle. The theoretical physicists, they say that maybe this Axion is a candidate for the dark matter. The fun fact about Axion is that it was actually inspired by the washing powder detergent, its name. So people who discovered or who discovered that Axion, there was an interesting fact about this axion. It was again hypothetically, people thought about it because it can be able to solve a problem in the standard model of physics. So it basically resolves the symmetry problem in the standard model. And so people say that just like the washing powder, it swipes away the sweeps away the dirt, the axion sweeps away the problem of symmetry in our standard model, and that is why they gave this particle a name axion. So anyways, it is hypothetical. It is not discovered yet in our experiments, but it is there in the, as far as theoretical calculations are concerned. And it is considered to be another candidate for dark matter because again, its properties matches with the dark matter particles. But it is more trickier to discover than WIMPs because it is extremely light. It's trillion times lighter than the electron, which itself is very, very light, and it's weakly interacting. It was theorized to be created at the time of Big Bang. And after the Big Bang, it was supposed to exist throughout the space, even created in stars and escape into space like other lightweight particles like neutrinos. It also has a very special property, which was discovered in 1983 by Professor Perry Skikiev, that in the presence of electromagnetic field, these axion particles sometimes spontaneously convert to easily detectable photons. And photons are basically the particles of light. So if this axion exists, if we prove that this particle exists in nature, it's very easy to detect that particle because we just need a very strong electromagnet, and in the presence of that electromagnet, it can easily be detected because it converts into visible photons. So in a way, it is easier to be detected as far as WIMPs are concerned, but of course, there are some challenges for discovery or creation of this particle in our labs. So now let's talk about some experiments which are hunting for this dark matter. So from space-based telescopes to underwater detectors, scientists are leaving no stone unturned in their search for hints of dark matter. People basically are trying to figure out this dark matter or are hunting this dark matter in two ways. First is known as the direct search. So in this kind of search, dark matter particles bump into the target material and scatter off atomic nuclei, resulting in a measurable nuclear recoil. And from that recoil, they recreated what kind of particles, like from their properties of mass and their decay width, etc., they can be able to search this dark matter. So these kinds of direct search experiments, they are underground experiments because we don't want any kind of background noise from the visible matter stuff. Because if that dark matter exists, it interacts very, very weakly with the visible matter. So we want to escape these experiments with the visible matter particles, which are coming from the cosmic rays. So that is why they are built underground to avoid the background noise of visible particles. And in total, right now, there are 31 experiments which are performing this direct search. Second search is known as the indirect search. So indirectly, what happens? So if there is a dark matter particle, it annihilates. And after the annihilation, it is converted into the particles which we know. So we are trying to search those particles which actually exist after the annihilation of the dark matter. So that kind of search is known as the indirect search because we are not directly looking towards the dark matter, but from the annihilation of dark matter, the particles which are created, we are trying to figure out those particles. And from their properties, we can be able to say what kind of their parent dark matter particles would be. These indirect search experiments are conducted with ground-based or space satellite telescopes, and in total, 15 experiments are built for this indirect search. So there are some examples of direct search experiments. One is in the University of Washington, and it is known as the axion dark matter experiment. So this experiment is basically searching for this particle axion, which is one of the dark matter candidate. Another one is in northern Spain and is the Argon dark matter experiment. Then we also have a direct search experiment in Canada, Ontario, which is the Picasso project in Snow Lab. Then the most famous one is the Large Hadron Collider, which is working in Geneva, Switzerland. So these are some examples of direct search experiments which are built underground. For indirect experiments, we have one at the South Pole, which is the Ice Cube Neutrino Observatory. Then there is one in Virginia, USA, Heavy Photon Surge Jefferson Lab. Then another one in Northern and Southern Hemisphere, which is Cherenkov Telescope Array. And last but not the least, one is in the underground sea experiment that is built under the Mediterranean Sea, and that is Astronomy with Neutrino Telescope and Abyss Environmental Research. So these are some examples of direct and indirect search experiments. And then I would like to conclude my talk with this quotation of famous author Laurie Moore. So according to her, a dark matter is a page-turning thriller of every sort, psychological, sociological, epistemological. Plus, it's really scary. Thank you so much for listening, and questions are welcome.
Okay. Thank you very much, Mahumm. That was very interesting.
Thank you.
If people have questions, maybe you can just indicate in the chat and we'll call on you to unmute and you can ask your questions. I can maybe start. So you said that axions, one of the possibilities is that axions might actually be produced in stars.
Oh, yes, there is a theory. Yeah.
So does that mean that the amount of dark matter in a galaxy would be increasing? Is there, is it enough? Would there be enough dark matter produced in stars to actually change the sort of gravitational effects in a galaxy, or is it a small effect?
Well, there is a theory that axions may be a dark matter candidate, and it created in stars, and then it escapes into the space. So it doesn't stay in that star, but it escapes. So, and right now we have around 26.8% universe, which is made up of that dark matter. So of course, if it is proved that there is axion and it is created in stars, so that means, of course, that the amount of dark matter is increasing as soon as we have more stars appear.
Okay, well, that'd be interesting. Sue Hart has a question. You want to unmute and ask your question, Sue? Can you do that, or do we have to unmute? Do we have to do something to let?
Okay, is that better?
There we are.
Okay, good.
Yeah.
Yeah. Thanks for that talk. Fascinating. Just curious, you were talking about two ways of hunting for these dark matter particles, and one of the ways you mentioned was ground and space telescopes. And I'm just curious, how do we see if a dark matter particle has annihilated? Because I think that's what you were saying is the kind of clue, if you like, the indicator in these kinds of experiments. And I just wondered if you could elaborate on that a little bit, because I think on your overhead you said that, you know, with these space telescopes, presumably and ground, the way we try and detect these dark matter particles is, I think the words you used was, you know, we're looking to see if a dark matter particle annihilates. And I'm just wondering, how do we do that? Like, how do we, what are we looking for? What are the indicators in the sky in that case?
Okay, so yeah, if there's one possibility, if the dark matter particle annihilates. So when it annihilates, it will be created into those particles or that matter which we can actually see. That matter would be the visible matter, the normal regular matter. And from the properties of that regular matter, if we if we have something which annihilates, and we can be able to, by using different conservation relations like energy conservation and momentum conservation relations, we can predict the properties of the original particle which was annihilated. So we are basically trying to figure out from those properties what kind, maybe that particle is dark matter particle or some regular matter.
So it's sort of like a residual category then, is it? In the sense that if you can't detect what it is, if you can't figure out what it is, then it might be or possibly be or probably is a dark matter particle. Have I got that right? I'm not a scientist, so I'm just trying to understand it. Yeah, okay. All right.
Yeah, it's like that.
Yeah, okay, thanks.
I think also they aren't necessarily visible light telescopes that would be used.
Right.
I mean, it could be in
X-rays or something, gamma ray.
something like that.
Okay, yeah. Do you know if the James Webb telescope is going to be doing some of these experiments as well into looking for dark matter? You know, this, yeah, the new one that's going up, or it's in orbit, isn't it now?
Cherenkov telescope?
Yes, the new James Webb telescope. Are they going to be doing some of these experiments with dark matter, or scientists who've rented time on it, I should say?
Yes, maybe, because here, the telescope which I mentioned here, these are just a few examples, but there are in total 15 one. So yeah, there are other also as well, which are working.
Okay, thanks very much. Great talk.
Okay,
Thank you so much.
John Peddle had a question.
Hi there. I'm just wondering if dark matter gets captured and trapped by black holes the same way regular matter would.
Oh, yeah, that's an interesting question. And yes, it would be, because dark matter has a property that it is matter actually. Just we can't see it, but it can be captured by the that black hole because it has gravitational effect.
Okay, cool.
But right now we don't know that how it interacts with the black hole, or how it can be captured by the black hole.
Okay.
Okay. I don't see any other questions, so if not, maybe we can thank Mahumm again for a great talk. And
Thank you so much.
thank you. Okay, so I will now share my screen again, and we can go through some member observations. Remarkably, there were some, even though it doesn't feel like we've seen the sky very much since our last meeting. And so we'll run through, and I'll invite people to say something about particular observations that they've sent in. I've sort of asked people that have sent in multiple observations to pick out a particular one to talk about, but I may put a few people on the spot anyway. So can you see this?
Yes.
You can see my screen. So we had a lot of observations of Comet Leonard before it moved from the morning sky to the evening sky. But a couple of intrepid members still managed to look for it in the evening. And so this is a picture. There wasn't much time to see it in the evening because it was very close to the western horizon and set very quickly. But this is one that Randy took. And I don't know if you want to say just a few words about this one.
It was a wind chill of -16 at that time. And by the time it got dark enough, I was frozen. Cameras were starting to fade. So I did manage to get a few pictures of the smudge. It's not much of a comet on our side of the air. The time on the other side, it got much better. Anyway, it counts as another comet I've seen. So,
yep. And let's see, about the same time, I think, I hope I got the date right here. Jim, do you want to say something about this picture, the double cluster?
Yeah, the double cluster was a target that I was using to basically test the setup of the telephoto lens that I was using for astronomy. I've been having various issues with it, particularly with respect to pinched optics. So I was taking test shots. So this just happened to be one of the shots. This is taken with a a narrow band filter, so the colors are all a bit off. But anyways, this is the double cluster is in Perseus, and Perseus is a hero of Greek mythology, and has several heroic feats to his credit, one of which is freeing the princess Andromeda from being chained to a rock and being menaced by some sort of a sea monster. And in any case, these particular clusters here make up the jeweled handle of the sword of Perseus in the constellation Perseus. So it's in the dark sky, it's a naked eye object. So it can be seen with the naked eye. It's not too far from us. It's approximate, there's several thousands of stars in each of these clusters, and it's not too far away. Surprisingly, these star clusters are moving towards us at a speed of about 30 kilometers a second. So there's lots of very large supergiants, red stars. You can see in this particular picture a little bit of the yellowish red supergiants. But most of the stars are very young blue giants, supergiant blue supergiants, and they're about 13 million years old. So this is a very, very young cluster. Yeah, that's about all I've got in terms of the astrophysics of this cluster. It's a popular object, and the large number of stars makes it a good target for testing telescopes.
Yeah, it's one of my favorites. Thanks. So we've got a lot of moon pictures. Chris, I forget. Well, do you want to just say a few words about this one? I think I've got some more moons for you later on.
Just a couple. Yeah, we've had a very eventful fall, so I actually haven't gotten out into the little observatory in a long time. But I did get a chance to grab a DSLR with a stabilized telephoto on it, and just throw on a coat and run outside into the driveway and point at things. So I pointed at the moon one evening, full moon, and took a bunch of exposures and added them up, tried to sharpen them up a little bit. There's a bit more detail than is visible here, but yeah, anyway, so that's the full moon. The details are on the left. It's just a handheld Canon digital SLR, the 300 millimeter lens on it. Actually not stabilized, sorry, that's right, that would be my other lens. So it's literally shoot a whack of frames and hopefully you catch a few that aren't smeared. Again,
Okay, very good.
Yep.
We actually managed to get 2 full moons between the last meeting and this one, so there'll be some more moons later on.
There you go.
And this was actually the one I wanted you to talk about. You want to say a few words about this, because this was quite nice.
Thanks. Exactly the same thing. In fact, exactly the same day, which I think was part of the point why I did it. I happened to be motivated that day. The full sun was also out in the middle of the day, and I took the same camera and the same lens. The camera had a Botter solar screen filter put over the front of it.
So we should say to everybody right now, they should know, but just in case, don't do this without a proper filter.
Yeah, critically important. If you try to point at the sun with a telephoto without a filter, you will probably hurt your camera. If you do it with your eye, you will have one less eye. If you do it with both, you'll be blind. We have a center member who used to say you have 2 chances to try it. Don't do it. Yeah, so the sun is actually pretty much white. I mean, paper looks white when it's illuminated by sunlight. Everyone likes to think of the sun as yellow, perhaps usually because when you look at the sun and you can see it without being blinded, it's just above the horizon. Anyway, I took the white image and I tinted it yellow. And there were some sunspots you can see I think the sun's a little busier now. People with solar telescopes can see the hydrogen alpha prominences. This is just a white light image. So, and there you have it.
Yeah, the sun's getting to be a lot more fun these days.
Yeah.
Okay, so Bernard, out in Central got a, or more towards Central got a, another one of the last pictures of Comet Leonard. You can see that we only had a couple clear days because all these pictures are clustered around a couple of days. But the one that I want to ask Bernard to talk about is this one. So Bernard, are you there?
Yes, I'm here.
And the posting on the talk group was around January 7th, and it said about a week before. So I don't actually know the date. I'm kind of guessing, but a week before January 7th would have been around New Year's. But I guess we're looking at Venus there and Mercury there. Is that right?
Yes, yes. It actually was on New Year's Eve.
Well, there you are. That's close.
Yeah, I went to the cabin on New Year's Eve and wasn't expecting to get any pictures because it was a lot of cloud hanging around, but it did clear off just as it started to get dark. So I just took my DSLR camera with a 55mm lens and put it on the rail on the patio actually, and pointed it towards the southwest as the sun was setting, or after the sun was setting. And I was lucky enough that I got a picture of Venus and Mercury. And to my surprise, they were setting almost exactly the same time. So I thought that picture was, yeah, it was about a 15-second exposure. So it's a little bit of a trail, I guess, on each one of them, but the horizon looks fairly clear. But I looked it up after and on Sky Safari, and there was 90 seconds in difference from the time that Venus set until Mercury set, or maybe it was the other way around. I'm not quite sure. There was 90 seconds different, but they looked like they were going down about the same time to me. And I did look it up, and it said they were about 6 degrees difference in the horizontal direction, I guess, along the horizon from one to the other. So, you know, I kind of thought that was sort of something that you didn't see very often. So I looked it up and I couldn't see too many times in the past, or I couldn't see much information on it really, where both of them were set in the same time. But I did look up on Sky Safari as well. In their orbits, Venus was headed towards the sun, and at that time Mercury was headed away from the sun. So I guess it just happened that they were crossing the horizon on my point of view at the time. I also looked up in Sky Safari that on the swing around that current swing, I guess you call it, or orbit around the sun for both of those planets, Venus went as high as 21 degrees in altitude, but Mercury only went 1.1 degree at 36 minutes above the horizon. And on the same swing, I guess, from my point of view, Venus went as far south when it was highest to 214 degrees, which was, I guess, around from north going east, around that direction. I changed my settings on Sky Safari from the equilateral coordinates to horizontal coordinates to get that. And Mercury was at 234 degrees. So that was about 20 degrees difference that they did swing. But right at that time, they were only about 6 degrees apart. So just thought nice. I was pretty lucky to catch that at that time. I think just you know, two of them setting at one time. So anyway, There it is.
Getting both of them in one picture is pretty impressive, and getting them both just above the horizon is pretty cool. So thanks a lot.
Okay, thank you.
And Jim wasn't able to be with us tonight, but he, the way he put it was he had to dust off his stuff in his little observatory, literally. So he was just sort of checking things out. So he sent us a few pictures, the Rosette Nebula, this with an 80 millimeter telescope, and this camera. I didn't have much detail about how many exposures or how he processed it. The Leo triplet, so 3 galaxies near Leo, same camera, same day. M42, same setup, so the Orion Nebula. And about a week later, he went back to the Rosette Nebula, but now he was using a narrowband filter that only does the red hydrogen alpha, but with a monochrome camera. And so this is the sort of thing he would put together with images through other filters and build up a an image from that with information about emissions from different atoms, different ions. So unfortunately, we don't have Jim here to give us more detail about that, but as always, it's fun to admire his work. And then a couple days ago, we had another full moon, and miraculously, it was again not too cloudy. So Robert took a shot of the full moon, and Randy did as well. And so I'm going to ask Randy just to say a few words about this. I think one of Randy's hobbies is to try and get to the right place to get something in front of the moon. And I was walking home that night and watching the moon come up and wondering where Randy actually was, because that was just coming up as I was walking home. And I figured he must be over somewhere close to the South Side Hills trying to get a picture. But
well, this moonrise that day, of course, it's the smallest moon for the year, and it was before sunset, so it's tough to get a good image of the moon in a clear blue sky like that one's coming up. In this particular case, I was in Mount Pleasant Cemetery up off of Black Marsh Road. I couldn't find a suitable site to actually get the shot that I wanted, so instead I kept this one. The moon is quite soft when it's rising, and jaggedy, I call it. It's not till it gets up maybe 45 minutes till it starts getting very nice, clear, and precise pictures. But at the same time, I also had a new camera for Christmas. It's a full frame mirrorless, so I wanted to compare and try some of that stuff. But while I was trying to catch the moon rising quickly, behind me there was a beautiful display cloud. There was a big cloud bank coming in, and the sun was just going down through it. But above that, there was a huge band of cirrus cloud all the way across the sky. Parts of it looked like snow, parts of it looked like smoke, whispery smoke. So I really didn't post any of those pictures, but
well, you had one, and I didn't grab that one,
no.
but
So
it was there in the
swinging around, shots of clouds back over to the moon and back and forth. So it was quite cold as well that night. So we'll see.
So the bumpiness on your moon, that's atmospheric then?
Yeah. As well, at this time, this was about 5 o'clock in the evening. Full moon was actually about 9 o'clock that night. So that's probably
It might be a little bit of topography, but
so we don't usually get much around exact full moon time. So
okay. And Jim Stacy was out That was the same, yeah, it's full moon, so the same night. So Jim, do you want to say just a few words about this? You were comparing two lenses?
Yeah, this was just taking two of my legacy lenses on the, and one was a 80 to 200 millimeter Canon lens, and the other one was a 300 millimeter. The only thing of interest here was that these were taken handheld the same night as Randy took his beautiful shot. But I was just testing the sharpness of the two lenses. Because I'd like to use them both for astronomy.
So they're called legacy lenses because you have to have received a legacy to be able to get them?
Well, no, these are you can buy these rather cheaply on the internet, actually.
Okay.
But you know, what I call a legacy lens is anything that dates back to the 80s or 90s. So these are 30, 40-year-old lenses. So these two particular lenses both have fluorite lenses, which is a particularly expensive type of crystal, artificial crystal, used in very, very few lenses, actually. And yeah, and so anyway, I just thought I'd just try to test them out, and I thought that they performed rather well, actually.
Looks like it. Hi to Amber.
Anyway, I'm gonna mute here now.
Okay, thanks, Jim. Okay, so those are the submissions or what I could pick out of the talk. And now, Nikolai, can you do the sky this month?
All right, so this is the sky this month document that you can find on our website that I update every month. And it shows you what's available to see in the sky from Newfoundland and more so St. John's this time of year. So starting off with sunrise and sunset times. Currently sunrise at 7:40, sunset is at 4:42. So the day continues to grow slowly, but getting there. Here are the rise and set times of the solar system planets as well as Pluto. This is a picture of the sun taken today. So that essentially confirms the high activity that we've been seeing, as you saw in the picture that was shared this evening. And if you've been following the talk list, people have been talking about how active the sun is. Still the case. You can see 4 groups of sunspots with 2 of them about to rotate out of view, but still, you know, good bit of activity. And again, never look at the sun without proper filters. In terms of planets, evening planets right now, we still have Jupiter and Saturn. They continue to be somewhat of a pair traveling in the evening sky into February, and they can easily be seen in the south. Still somewhat well placed for telescopic observing early in the evening, setting about 2 to 3 hours, I guess, closer to 2 for Saturn and closer to 3 for Jupiter after the sun. Uranus and Neptune, they had their opposition dates late last year, so they're still visible in the early in the evening sky. And then there's that's actually my bad. Mercury shouldn't be under evening planets. It should be, I guess, more so on morning planets. It's currently undergoing conjunction, which happens on the 23rd, but then it returns to the morning sky, which will not be a very favorable opposition. But then it goes back into an evening opposition in the spring, which will actually be the most favorable one of the year. Usually the spring evening oppositions are the best for Mercury. So morning planets, Venus, which underwent conjunction with the sun on January 8th, and now is slowly re-emerging as a morning star, rising just before the sun. So we're pretty close to that to that date, but usually even just a day or two after the conjunction, it becomes visible. So kind of a question here is if anybody, how soon can you spot it after its conjunction, and have you spotted it yet? It's something that I've always enjoyed doing, seeing how soon can you actually see it after it reemerges. I haven't seen it, but maybe someone else has. Mars is also a morning planet now and rises about 2 hours before the sun. It will slowly brighten and get larger throughout the year as it works towards its opposition in December. But for now, it remains too faint and small to observe with much detail. So that's the planets. Here's comets. The latest update on Leonard from this table is from the 3rd, so I don't know what's happened since then. I haven't really bothered since it got really faint, but then not much else on the go beyond that. And then there's the asteroids, 5 brightest for us, supernovae, of which currently the brightest is magnitude 11.4, so not very bright. Meteor showers, there's nothing on the go this time of year. January and March are pretty quiet months for meteor showers. It's not until April that we start to see the next relatively bigger one. And here's a list of the biggest or brightest, I should say, objects for January and February for telescopic and for binocular observing. M42, the Orion Nebula, being main target this time of year, which brings me to the observing challenge for January, which is an easy one because the last one was tough when I asked you to see the comet after it had passed into the evening sky. So now I'm compensating and giving you an easy one. So try to resolve the trapezium of the Orion Nebula. All you need is a telescope greater than about 3 inches. So you should be able to see what appears to be a central star, with, I guess, with the naked eye, resolve into 4 stars that resemble a trapezium. So I'm sure most of you have probably done that at some point, but here's another incentive to do it again if you haven't done it in a while. So that's your observing challenge. And I should probably ask, other than Randy, has anybody completed the last observing challenge, which was to see the comet Leonard after it became an evening object?
I had a smudge similar to Randy's, same night, but I wasn't even as sure about it as Randy was.
Yeah, I was out on the same night and took some pictures, and I do have a smudge, but I also have another smudge on that picture. So then it you're starting to question what's real and what's not real.
I had a smudge in the right place. But
oh, that's encouraging. Here's a list of International Space Station passes for the next month. Also, I was able to add something that Marcellus sent me, and thanks Marcellus for bringing that to my attention. Those are transits of the Tiangong satellite across the sun and the moon happening. I believe he said that was plotted for Portugal Cove. So those occur on the 3rd of February and on the 6th of February. So it will be, the satellite is much smaller, or apparently much smaller than the ISS, but when it transits across, especially the sun, you should be able to take a picture. It's a very, very quick transit. It's only a 2-second transit, so it's literally a blip, but definitely a fun challenge to try to capture. I don't know, Marcellus, if you had any other information that you wanted to share about this.
No, let people know where they can find that website so you can put it for your own backyard or whatever.
So it's transit dash finder.com. Is that correct? Yeah.
Yes.
So it's a
Oh,
good,
you can see it right up there, up at the top of the screen there.
Oh, yes, that's right here. So this could be another observing challenge. However, you don't get much of a chance with the weather here. You only have 5 seconds total in which you can see those two events combined, and yeah, that's it. Here, there's no observing sessions happening right now. No change to that. Here are the observing calendars for January and for February, and that's all I have.
Nikolai, I've got a quick question. In your January binocular objects, you had Kemble 1. Is that the Kemble Cascade?
I believe so. I want to go and double check to be sure, but I think that is what it is. Probably someone knows better than I do.
Okay, yeah, it's I've only seen it once, and it certainly is best in binoculars, but it is a lot of fun.
Oh, yeah.
It's basically just a line of stars, very sort of surprising arrangement of stars.
Yeah, I don't know if there's a Campbell 2 and 3, etc., but there is a Campbell that's a line of stars, and it's exactly that.
Okay, thank you very much, Nikolai. So just a few items. Our talk next month is by Susan Redmond, who's a PhD student at Princeton, and she's going to talk about balloon-borne telescopes to the stratosphere and beyond. And I haven't heard her speak about this, but I know that these are very interesting devices. I'm not sure if this one is at the South Pole, but a lot of them are. Some of you have already seen postings about this, but Anna O'Grady, who's a member and talked to us, she's talked to us a couple times, talked to us last year. I guess she's getting pretty close to finishing her PhD, and the Dunlap Institute at the University of Toronto did a 15-minute video about her research, which I think is just excellent. A few of us have seen it, or maybe lots of us have seen it. She's a very good speaker, and it's a very well done video about her discovery of super asymptotic branch AGB, asymptotic giant branch stars. So she was looking for Thorne-Zhitkov objects, which are stars with a neutron star in the middle, and we're probably the per capita, there's probably more awareness of Thorne-Zhitkov objects in St. John's than anywhere else in Canada, because we keep hearing from Anna about them. So she was looking for that and didn't find that. She found these super asymptotic giant branch stars and sort of identified the first population of those. It's quite a big deal. And so the video talks about how she looked for one thing but found something else, and how that's kind of how science works. And I'd encourage you, if you just go to YouTube and search for Anna O'Grady, it'll be there. It'll be the one that comes up that says something about stars. So I think it's pretty easy to find that one. And we've already talked a little bit about some of the issues with getting some things from the national office, and Randy commented on this, and we've gotten a little bit of information about these issues in the newsletters and bulletins that I mentioned at the beginning. And some of the issues that they're dealing with are they've moved offices. There's been some staff turnover, at least the office manager, the membership coordinator, and the education and outreach coordinator, who was Jenna Hines. All those people have moved on and been replaced. And in an organization, that always stirs things up a little bit. The bulk order of calendars that we made did show up a little bit after New Year's, but we've been hearing that there are still some issues with handbooks and calendars that people ordered as part of their renewal. So it says mostly resolved, but I think we're not quite resolved yet. But Marcellus has been doing a great job, and Randy sort of keeping track of this, and we'll hopefully see things sorted out in the next few days, perhaps. They've blamed Dieppe, but I don't think it's just Dieppe. And then hopefully next year they'll do something different. That's sort of what I had for the formal agenda. But I'm going to stop sharing now, because I think people might have some questions. This is the first meeting after the holidays. People might have some new equipment. There might be some technical questions. So this would be a good time if people, if we don't have questions, we can just socialize a little bit. But if visitors, or if any members have questions about stuff that they got, or questions about things that they saw, now would be a good time to raise them. You can either unmute yourself and talk, or indicate in the chat that you've got a question, and we'll wait and see if anything happens. And if not, we'll sort of dissolve and people can hang around and chat a little bit if they want. And I think we're still an hour away from the next group that wants to use the Zoom channel. Is that?
Wendy wants to ask a question, I think.
Oh, yes, please. Go ahead. Wendy? Oh, you're muted.
I was
There you
told
are.
that several times today in my grade 5 classroom. Miss, you're muted. Very interesting meeting. I feel that if you pardon the pun, everyone here is light years ahead of where I am. I love looking outside in the night, and I got a new telescope for Christmas. I was given it, so it was not something that I did research on and you know, made a decision about the purchase. So I kind of need a little bit of feedback maybe on the capabilities of it, because I'm certainly not ready to do what everyone here seems to be doing as naturally as breathing. But
well, we all started it, and some of us not that long ago. So take it away. Tell us what you got and what your questions are.
well, I was quite pleased with myself from going from teaching grade 5 science on forces to following the talk on dark matter. That was my accomplishment for today. So I'll just hold my camera here now and just, this is what I have, a Celestron Astromaster 70. I don't really know much about it except what the possible price was from Canadian Tire. I haven't attached the other things here, but I'm going to have to use the information online to put the last few things on. There's 2 lenses here, I guess. There's a 20mm and a 10. That's, I guess, whatever is built into the end of it is what I'll learn about after. It came with a CD and stuff. I have another telescope in the basement, but I don't think it was as expensive as this one, and it was probably about 15 or 20 years ago. So I don't know if anybody has any information, if that's like what I'm going to be able to see with that. It seemed like I could see the moon on the older telescope, and not really enough time to research what else I might be able to see. But a telescope is only going to show you stuff if it's collecting light from objects in the sky. Is that correct?
Yep.
Because obviously you're not going to be able to see anything in the pitch dark. It has to be able to capture enough light to, you know, unless it's in the daytime and you're looking at the full moon in the day or something. So yeah, I guess I'm just at the beginning of seeing what this thing can do. Like, is it, it's not going to go back to the store now because there's just some Christmas gifts from people you just don't return.
Right.
So, you know, does
Well,
anyone know?
the two eyepieces you have,
Mhm.
they're different. They'll give you different magnifications. And the magnification is basically the length of the telescope divided by the size of the eyepiece. So you've got a 20 and a 10. And you'll probably find that the 20 is the most useful with that telescope. I think there are people who know a lot more about telescopes than I do, but I expect with that telescope, the 20 will probably be your best bet. Chris?
Yeah, I saw your telescope very briefly there, Wendy. So it's that telescope would probably be fine for the moon and brighter planets like Jupiter and Saturn. The 20 will give you a wider field of view. It looked like the telescope was probably 70 millimeter diameter lens, and I'm guessing 10 times that for the length, and divided by 10. So maybe the 10 millimeter will give you 70 times magnification. And that's good enough to certainly to see the rings of Saturn and the moons of Jupiter and maybe some belts. And you can point it at bright star clusters and this sort of thing. You'll want to put that red dot finder on, and the CD will explain how to use it. And you'll want to, again, safely, don't ever point at the sun in the daytime, but in the daytime, or maybe dusk or morning or something, or when you're outdoors.
They took care of that already.
Excellent. Good. Good. Save the eyesight. To line up the red dot finder, there'll probably be either some screws or some little Allen key hex bolts, and then maybe a tool with it. But you put it on top of the tube, and then you want to make sure the red dot is when you look behind it, you'll see it, and turn it on, you'll see a red dot, literally in the sky. You want to make sure the red dot is on top of what the telescope's actually looking at. So you point it at, say, the top of a telephone pole a mile away, and it doesn't move, right? So you can just sort of leave it there and adjust your finder until the red dot is on the telephone pole. And that one thing will make using this telescope much less frustrating, because then you can just sort of, at night, you can put the red dot on something interesting in the sky and look at the eyepiece. And Mike's right, the 20 would be better to start with because it'll have a lower magnification. You'll see more sky and you'll be able to find things more easily. And yeah, after that,
Well, you should
uncle, I guess.
probably start by going to the celestron.com website. If you're missing any manuals, for example, they're all there. You can download. They'll also have some videos. Another great resource would be YouTube. And if you just search for Celestron, you know, Astromaster 70, I'm sure you'll find 3 or 4 at whatever level that you need, how to put it together, how to cite things and what to look for. And they advertise this as for the solar system. So as the people have said, Jupiter and Saturn and the moon should be very easy and great targets for you.
And I think it'd be fine. It'd be good for the Orion Nebula too.
Yes,
I
actually,
think you
no
get
problem.
a great view of the Orion Nebula with that.
Yeah.
Chris was saying about lining up the finder, that the finder makes a big difference during the day. Just be really careful that it's not anywhere where it says don't point at the sun, but also be careful that it's not somewhere where the sun is going to drift across when it's just sitting there. The sun isn't going to move across in front of the telescope. I bought a used bigger telescope from somebody, and when I opened up the box of accessories, and even now, many, many years later, there's a very strong smoky smell. He had the telescope just sitting out during the day, and the sun went over top, and there was a cap on the eyepiece, and it melted the eyepiece. And when I got it, there was a melted the cap on the eyepiece, and that was in the box with everything else. The smell still hasn't gone away, so that you have to be very careful about that. So when you're using it out during the day, I would say point it in the opposite direction from where the sun is, just to be safe.
And
The sun at your back.
daytime is also useful for getting used to the moving of the telescope, which way the controls work. I don't know whether you got an erecting prism with that, but typically in a telescope, things will be upside down and maybe even backwards. So it might look odd to you but daytime is good to get used to the controls, the fine tuning of the eyepieces and where it's actually
So
pointing.
that's what that thing is for, the erector lens or
Yeah.
something.
Well, that's so you don't,
right side, okay.
Yeah, without that, you've got to be down and looking straight through the tube, but that inverts the image up so you can push your eye down at it.
So what's a Barlow lens?
That'll double the magnification.
Mhm.
Well, it's a 2 times Barlow. That'll just double the magnification of
Yep.
your eyepiece. So if you've got a 10, it makes it into a 5. If you've got a 20, it makes it
Okay.
the same as a 10.
Yeah, it just saves you from having to buy a whole fleet of eyepieces as well, right?
Well, that was with my old telescope. So yeah. And I was going to say Orion is one of my favorites. So I can just stand in my driveway and see just about the whole constellation
Well,
clearly.
You're in for a treat then if you look at the scope through it. Now you won't see any of the images like we've seen tonight on these
No.
pictures, but you should be able to see some smudgy stuff.
Yeah, but
That won't last for much longer, will it? That Orion is as visible as it is?
into March.
Yeah, and then
Okay.
it'll be back again in August.
Mm-hmm.
Yeah.
Yeah, but a different over the trees in the back of my house.
Yeah, that's the
So
problem.
I'll see it
So
then.
the next thing you got to get is a chainsaw.
Yeah.
I'm close to that myself.
Yeah.
I'm going to put in about setting up her finder scope.
Mhm.
Make sure you find something in the main telescope first, and then try and align your red dot to agree with it.
Yes.
Not the other way around.
That's the
Yeah.
important
Thanks,
part.
Marcellus. Yes.
Even a pole
Oh.
line, top of a pole even.
Yeah.
I've got another important thing about the red dot finder. Make sure you turn it off when you're finished.
Yeah.
with it,
Yeah.
Yes.
Or
because
buy a-
it's you don't know that it's on,
yeah.
and it's got a little button battery in it. And
Yeah.
if you're like many of us, you may end up having to replace the battery every time you get it out if you don't get in the habit of turning it off when you're done with it. It's very
You
easy.
stand in front of it and look back. You can see the little red pinpoint in the black plastic. You want that to go off. You want to hear a click.
Okay.
Otherwise, you will have a dead finder next time you observe.
Oh, Jim was trying to hold something up, but your blurring background is hold it next to your face. 'cause-
Yeah. Up
'cause
against
your
your
face
face.
is in.
Yeah. Guide
Okay.
to. No.
This is I was just going to suggest the RESC has several beginning books that are truly excellent. And the one that I really liked was
Explore the universe.
called the Explore the Universe Guide, and it does explain a lot of things about beginning astronomy and the tools, binoculars, and so on. I just quickly looked at it, and it just basically introduces you to the constellations in the sky, and it's a rather good book, and it's available through the RESC website.
I've purchased a few books up through the years. that were basically for myself as much as my kids. So there's lots of information to get me started. But like I say, the first thing is to get the telescope put together, see what I can see with that, because you can certainly learn a lot more than what your telescope will actually ever show you.
Yeah.
So, yeah.
Did I send you any material? Did you ask me for any material?
No, nothing yet.
Okay. Send me a note, would you, on the info address, and I'll send you a Sky News magazine and a moon globe listing and some of those things. That's what I normally send out to people. The RESC has a certificate programs as well. If you join, you can apply and do certificates for the moon and binoculars with the moon, things like that. There's also a very thinnish book, but it's 50 things to see on the moon, which again you can easily use at the telescope to look for. The moon is just not just a blank thing with potholes. There's a lot of things at different times of the month to see features.
But not on the dark side, correct?
Oh, I see the dark side all the time.
The dark side is different from the from the people say the dark side, but what they mean is the backside, or
but that's a sort of a challenge as well. There's one day a month or so that you can see a wall in a crater, or a couple of craters look like an X or a V, these sorts of things. So just give you something to get out to have a look at.
Sure.
And like I said, Jupiter and Saturn are always great. Next year or so, we'll have Mars back again. So when Mars comes close, it's always nice to try to have a look at.
Yeah,
Okay, well, thank you very much.
You'll be able to follow that through the year, actually, with the penultimate Mars observing experience being Christmas next year.
And once you get used to it and are happy with your observing skills, you can get little devices that you can put over the eyepiece, and then you can attach your phone to it, so you can actually take pictures of what you're seeing. Just proof. Again, it's sort of like a badge that I saw something.
Okay.
So send me an email, and I'll send you some material.
Okay, well, thank you very much.
Okay. And if we ever get back outdoors again, as I said, look up the YouTube thing. I'm sure you'll find some videos.
All right, thanks for all your help.
Okay, you're welcome. Thanks for
come back again next month with more questions.
Yeah, let us know how it's going.
I will. Thanks.
Good. So actually, I had a recommendation I was going to make. So I've been reading this book. I got it for myself for Christmas, sort of. Cynthia got it for me, but she didn't know what she got for me until we opened it. But I'm finding this a really nice book. It's got a lot of the stuff about it's a history of the universe in 21 stars and 3 imposters, and it sort of goes through stellar evolution using specific stars as examples, and it's a lot of the kind of stuff that I would have talked about in astrophysics without the math, and very, very readable. So, and I just got it at Chapters. I don't think it was very, very expensive. In the US, it'd be $14.95. So yeah, it's about $20 here. So if you're interested in a nice book about, stellar evolution, things like that, I could recommend that one.
Chapters not so long ago, and was surprised that there wasn't very much in the way of good books and materials for amateur astronomers.
Check the bargain bins. Sometimes you can get good stuff in the bargain bin, right?
Yeah, well, I just looked at the astronomy section only at that time. I have seen astronomy books in the bargain bins, but in the past, years ago, Chapters used to hold some relatively good materials for beginning astronomy and for advanced astronomy, for that matter.
Yeah.
But I was disappointed the last time I was in, which was about a month ago.
Yeah, Cynthia did get the new edition of the Backyard Astronomer's
Yeah.
Guide at Chapters.
Oh, is that
And we
right?
also got the RESC Almanac by Nikki Mortellello.
Mortellello, yeah.
That one.
Yeah.
That one.
Okay, I didn't see
Yeah,
either one of those.
So you may just have gone after I went.
Well, maybe, yeah, maybe it was all bought up.
Yeah.
Mike
Sold
bought
out.
up all the stock.
Yeah,
The new backyard book is quite a book. I don't know if it's a little pricey for a beginner, about $60 or so, right?
yeah, I think it's very, very, very good book though.
Cynthia said she got it for 45.
Yeah, and Night Watch as well. Yeah.
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 I've got a signed copy of that, Chris.
Ooh.
A new one or an old one? Probably an old one.
Several. He's always at the RSC conventions when we had them. So
Yeah. Yeah, no, I've got a old 90s version edition, so I was gifted the newest version, which is fun. It's a great introductory piece. There's lots and lots of stuff in this book. Highly recommended for anybody getting into it.
I was going to mention when Nikolai was talking about when Starlink, SpaceX launched their Starlinks like the other night, it's sort of becoming a challenge now to see the train the few hours later when they were letting the satellites fly. And it went over Halifax last night, and that Russian guy, forget his name now, he posted a picture of a train going across the sky.
So is it getting harder to see because they've done a better job of making them dark?
No, darkness is not working. So I think this new batch have got the lasers on them for communication as well. So
And Branson just set up a pile of satellites from the wing of a plane.
yeah, I saw that. It's not any old plane though. It's a huge, big 47, isn't it?
Yeah, no, but like it's like launching it like rockets from the other wing of a plane. That means it's going to get a lot cheaper, so there'll be a lot more.
Yeah, but he's basically.
They're all going to start running into each other pretty soon.
Yep.
Yep.
Yeah,
So
not necessarily a good thing either.
No.
the previous SpaceX flight, just even this year, launched 103 QB type satellites, including a couple of Canadian satellites. So yeah, 103. And I think there's another launch tomorrow, is it? It's going to be a record year for satellite launches, they say. So.
Oh yeah, well, Kessel syndrome is the predicted cascade of satellites hitting each other, and then the debris hits more satellites, and the debris and the debris, and the domino effect. Until that happens, yeah. But the Falcon 9 launches are fast and furious. Holy crow! And but they do it so well. I'm really torn. I like rockets, but I don't like what they're putting up into the sky.
And of course, they did Webb very well. And
yeah, Ariane Space launched Webb, and they did a fantastic job with that. Bang on. And they're thinking, I think, Mike, that they're going to have to use less propellant to get it at the L2 station, so that'll extend the mission. They were so accurate. And of course, they got it deployed.
Got Webb in his.
Well, marvelous. I'm envious.
It's not
so what kind of kit was that, Randy?
Well, actually, I saw an ad on Facebook, and I usually don't buy much from Facebook, but the fellow makes them. It's die cut. I thought it might have been aluminum because I have a number of aluminum models that are die cut, but it's actually just silver colored paper. So you have to be very careful. And if you want the address, it was only $20 or $30, right? So that's what I did over Christmas.
Very nice. Nice and shiny too. Is it really gold plated?
Oh, it is gold. Yeah, I actually hand painted some gold I had lying around. Right?
Oh, okay.
Yeah.
So you did that.
It's gold beryllium, is it?
Yeah,
Gold on beryllium.
Yeah.
very nice.
Mike, I noticed our speaker has left the meeting. Please congratulate her and thank her again for me and for us.
That was a great
Okay.
talk. Yeah, it was a great talk.
Yep.
And Anna, that YouTube video of Anna was something else. Obviously, it's a professional promotion job, but
Very well done.
Very
well
slick.
done, Yeah.
Yes,
There,
very well done. Very
there
well
was
done.
one amusing typo I noticed, however, and she was talking about depletion of helium in the cores of stars, and I think she was using a talk tool to do the subtext, and the talk tool thought she said cards. So
yeah,
it says cars of stars. So
yeah.
I thought that was funny, but otherwise very slick, nicely done.
Yeah, the Dunlap Institute must be very impressed with her to have put that effort into a video about her stuff,
Yeah.
and rightly so.
Gary, you're still alive?
Yeah, I'm still
Oh my
alive.
God.
You don't sound
This is
like
the
it.
best day I've had in about 29 days.
Wow.
We're
Holy
still on
smokes.
steroids.
Holy
and
crap.
buffers.
Jeez, Gary.
Yeah, the
Thoughts
rest
with
of the
you, Gary.
family only had about 5 days, but I even had the flu shot and all the shots. No, I had 9 days of just coughing and not getting any sleep, and I was having hallucinations. I didn't know if I was meeting people. I had to go to the ER twice.
Yeah.
I was
Holy
there
crap.
once, and they gave me puffers and steroids, and they said if it's not any better in 7 days, in 8 days I went back, and they said no, and then they gave me oral things that they said works with the thing, but I mean I find it hard just getting up the stairs.
Oh.
Oh,
And
really
And
sorry
this
to
is the
hear
first
that,
day
Gary.
that my coughing has really gone down. I've lost 25 pounds.
I
so
just
that's a
about to
good
say
sign.
that.
Wow.
You look like you lost weight.
Excuse me.
Hard way
Not a
to do it.
recommended weight loss
No.
program.
I'm
Well,
waiting till after my dental
yeah.
appointment on Friday to start eating some of my Christmas chocolate. That's my fear of the dentist, right?
Yeah.
Well, take care of yourself, Gary. Hope that you're on an upward trajectory now, but
yeah.
that's
Well,
that's pretty bad.
Get well, Gary.
We won't
Yeah,
get you to
that's
do
what
any
Ghaffar says.
lectures for a while.
no, I can't even. I'm still on page 1 of Sky News.
Wow.
I read, next minute I'm going.
Yeah.
So
That's it.
Robert, did you find that hut on the moon?
Oh, yeah.
Yeah.
It's right behind me, actually, but.
Big
Well,
rock.
lots of huts on that thing.
The big rock.
Yeah,
Yeah,
just it didn't even look very square once they
No.
got a picture of it.
Yeah.
Of course, the conspiracy theorists now are saying, "Oh, that's not the real one. They doctored the pictures, etc., right?" So, oh my.
Anyway, should we wrap it up?
Yeah.
Okay.
Okay, well,
It was a
Thanks,
good one. Thanks,
everybody.
everyone.
it was a good
Thanks.
meeting.
Yeah.
Thank you.
We'll
Thanks very much. It was great.
Thanks,
Bye.
everyone.
see you in a month, and I think we
Come
got
back
a
again.
great talk
Come back
coming.
again.
Clear skies, everyone.
Yeah, hopefully with no wind.
Nikolai's got to keep the snow away.
Yeah.
Yeah,
There
good
we
work
go.
so far, Nikolai, except for the wind and the cloud.
Yeah.
Yeah, that's
Beautiful,
right.
Friday.
Keep it
beautiful
going.
moon. Beautiful moon out there. But there's
Yeah.
some
Right.
snow coming on the weekend, isn't there?
Yeah.
That's right. See you all later.
Okay, bye, everybody.
Bye, guys.
Bye. Bye. I'm stopping recording.